Let's start with number systems. Imagine you have a box of cherries and you started counting them. So you had 1 cherry, 2 cherries, 3 cherries, 4 cherries, and so on. These are called natural numbers. If you finished all of them, you'd be left with 0 cherries. All of these put together are called whole numbers. In the past, you had -1 cherries, -2 cherries, -3 cherries. So when you include the entire set of numbers, they are called real numbers. Let's say you took a cherry and you cut this into 2 halves. So you would have 1/2 cherry and 1/2 cherries. If you cut it into 3 halves, you would have 1/3, 1/3, and 1/3 cherries. These are rational numbers that are denoted in the form of P by Q, where Q is not equal to 0. Now, why should we say that Q is not equal to 0? So, if you had a cherry and if now let's remember that rational numbers are of the form P by Q, where P and Q are integers and Q is not equal to 0. P and Q, they can be either positive or negative. And in fact, any number in the P by Q form can be represented in multiple ways. So let's take an easy example. So you have 1/2 as a rational number. This can also be represented as 2/4, 10/20, and so on and so forth. These are called equivalent rational numbers. If P and Q do not have a common factor, then P and Q are co-prime, right? Of course, one will always be a common factor. In the previous section, we saw that there are rational numbers when they are denoted by P by Q form, where Q is not equal to 0. What happens if a number is not represented by P by Q form? Such numbers are called irrational numbers. Where it cannot be shown in the form of P by Q, where Q is not equal to 0, and P by Q are, of course, integers. Here's something interesting. So if you had a number line and I identify a 0 on it and a 1 on it, in addition to this, I draw a perpendicular of size 1 and connect these two dots. The length of this is called √2, and on the number line I can draw using an arc, and this is what would give me a √2 on the number line, which means that rational plus irrational numbers both can be shown on the number line. All of these numbers, which is rational plus irrational numbers, they are called real numbers, and the number line itself is called real number line. Have you ever seen a chocolate wrapper? you'd see that there are prices written on it, and quite often, you'd see that the price is written as 10.50 or rupees, 100.79, and so on and so forth. Or even if you receive your Amazon orders, you'd see that the format of number is in decimals. Now, any real number can be represented as decimal expansion. This is a statement, and let's see whether this is true or not. Now, think of a number, let's say 10 by 3, and let's say we divide 10 by 3, so you get the decimal expression, and so on and so forth, and this basically continues, right? Now this 3.333 is called the decimal expression of 10 by 3. In another case, you have a number called 7 by 8, and let's take out the decimal expression for this. So you'll divide 7 by 8. Now here you see you got the remainder as 0, whereas in the previous one you got a remainder as 1, which was recurring. So you have two scenarios where you get a remainder of 1, and there's another scenario where you have a remainder of 0. Now, wherever the remainder is 0, we call them terminating rational numbers. On the other hand, where the remainder is non-zero with the decimals have a repeating pattern, they are called non-terminating recurring, and in cases where they are non-repeating pattern, we call them as non-terminating non-recurring. In each of these cases, the P by Q form or the number itself is a rational number. Here's a quick way to remember what we just learned. Now you have a rational number. The decimal expansion could either be terminating or non-terminating recurring. On the flip side, when you have an irrational number, the decimal expansion is non-terminating and non-recurring. Both of these numbers are called real numbers. Out of these real numbers, let's first look at rational numbers. The traditional commutative, associative, and distributive laws for addition and multiplication are applicable on rational numbers. I'll use some shorthands. Commutative, associative, and distributive for addition and multiplication are applicable. If we add, subtract, multiply, or divide any two rational numbers, we get a rational number. Again, of course, the division cannot be by 0. What about irrational numbers? In this case, the commutative, associative, and distributive properties of addition and multiplication are satisfied. However, when you carry out operations such as addition, subtraction, multiplication, and division, you may or may not get irrational numbers. Sometimes you could get rational numbers. Doesn't it seem interesting? So now let's look at some examples. You have a number 7 root of 5. If we had to determine whether they are irrational or not, we would first look at root 5 and convert it into decimal form. We'll see that it is non-terminating, non-recurring, and thereby 7 of root 5 is also non-terminating, non-recurring, and hence this is an irrational number. If we had to carry out certain operations, for example, 2 root 2 plus 5 of root 3, this is one number, and if we wanted to add this to root 2 minus 3 of root 3. Now how do we go about this? So what we do is this root 2 and this root 2 will come together. So you have 2 of root 2 plus root 2 in one bracket plus the root 3 will be together. You'll get 2 plus 1 of root 2 plus 5 minus 3 of root 3, thereby 3 of root 2 plus 2 of root 3. Further on, we could convert it into a decimal format, but for this instance, we will move forward. Let's look at an example of multiplication operation on real numbers. 6 of root 5 by 2 of root 5. We'll simply denote this as 6 into 2 into root 5 into root 5. 6 into 12 is 12. Root 5 into root 5 will give you 5, and thereby you have 60, which is a rational number. Let's look at a division operation. 8 of root 50 by 2 of root 3. If we had to divide, it would be 8 of, let's just put it in a simpler format first. Now 15 can be converted or can be called as 5 into 3. Now we remove or we segregate out root 5 and root 3. Divide by 2 of root 3. We'll cancel root 3 and root 3, and 2 will divide 8 to give us 4. So the answer is 4 by 4 root 5. Now this is an irrational number. Let's look at laws of exponents for real numbers. If we had to simplify 17 to the power of 2 into 17 to the power of 5, we'd add the exponents, which will give us 17 to the power of 7. Let's look at a different sum. 5 to the power of 2 bracket to the power of 7. In this case, we will multiply the two powers, and this will give us 5 to the power of 14. Looking at divisions, 23 to the power of 10 and 23 to the power of 7, here we will subtract the two exponents and 7 to the power of 3 multiplied by 9 to the power of 3. In this case, the exponents are the same, however, the base numbers are different. So here we will multiply 7 and 9 and we'll get 63 to the power of 3. Summarizing the laws of exponents for real numbers, you have e to the power of m into e to the power n, you add the exponents. Second would be like this. When it comes to division, you subtract the exponents. In this case, m is greater than n. And lastly, you have a to the power of m and b to the power of m, where exponents are the same but base numbers are different. Here you multiply the base numbers and take out the exponent.